Hello and welcome to the webinar presentation, Advanced Silicon-Based Anode Technology, Practical Implementations by Panasonic Tesla, ATL, and Sila Nanotechnologies. My name is Wendy Tam. I'm a Product Marketing Manager at Tech Insights, and I'm here to introduce our presenters and tell you a little bit about Tech Insights. Today's presentation will be delivered by Dr. Ali Kazelli, subject matter expert for battery at Tech Insights, and Trevor Isaac, product line manager focusing on battery and power. This presentation was previously recorded, but you could submit questions to be addressed during the Q&A session at the end of this webinar. Just click the Questions tab and enter your question in the text box. We'll be answering all questions at the end of the presentation. I will hand it over to Ali and Trevor shortly, but first I'd like to provide a short introduction to Tech Insights. Tech Insights is the most trusted source of actionable, in-depth intelligence related to semiconductor innovation and surrounding markets. By revealing the innovation others cannot inside advanced technology products, we provide competitive technical intelligence through reverse engineering to inform product roadmaps, market analysis to de-risk strategic investment in procurement decisions, and IP services. And now I will turn it over to Trevor Isaac.
Thank you, Wendy. Hello, everyone. I would like to first thank you for attending this webinar. As mentioned, this webinar will look specifically at 3 examples of recent consumer electronics products that are using advanced silicon-based anode technology. For companies that are familiar with Tech Insights, you might be surprised to see us covering this topic because most of you likely know us because of our product level teardowns or our detailed semiconductor analysis. Lithium-ion batteries are actually new technology segments as part of our subscription portfolio. But when I say new, it doesn't mean we haven't done battery analysis before, but rather it's new because we've now created a set of subscriptions to specifically profile the lithium-ion battery innovation that we are seeing in the consumer electronics market. Essentially, we saw enough continuous innovation that we felt it made sense to profile battery technology. To provide more context, before jumping directly into the discussion, I want to first talk a bit about the lithium-ion market and what do we mean by battery innovation. At this point, it's fairly obvious that the lithium-ion battery market is a big deal. Everywhere you turn, you hear news about batteries, be it in consumer electronics or electric vehicles. You see companies partnering and investing heavily. And this importance was really reinforced with the United States allocating $7 billion in funding to drive battery independence and strengthen the battery supply chain. Also, when you look at the market, the lithium-ion battery portion was estimated to be approximately $42 billion in 2021. And that's expected to grow by more than 4 times to $182 billion by 2030. And also, with all this talk about electric vehicles, it's interesting to remember that last year, consumer electronics still represented the largest revenue share with 40% of the market. But yes, the auto sector is growing very quickly and will soon overtake the consumer sector. Now, specifically around the area of today's discussion, we see the third item. As of 2021, there has been over $1.9 billion invested in startups specifically looking at silicon anode technologies. Okay, I keep saying battery innovation, but what does that really mean? If I look at that circle on the right, let's call it the battery value chain, there are a number of key characteristics that impact a battery's value. These characteristics obviously are different depending on the application. For example, a rechargeable battery for a phone versus a rechargeable battery supporting a home solar installation will have different needs. But in general, some of the key attributes are life extension. How many charge cycles can the cell go through? Energy density, be it by volume or by weight. Safety. How will the battery react to puncture, shock, or high temperatures? Will it result in thermal runaway? Cost reduction, fairly self-explanatory. Charging speed. How long is it going to take you to wait to get your phone charged? Or instantaneous power, which is important for cars, scooters, tools, where immediate high torque is important. Operating temperature. Does the temperature affect capacity? Being in Canada, this is one that affects me. I'm very familiar with that issue. Now, with that value framework in the back of our minds, let's discuss what catches our eyes in terms of the specific products that we choose to analyze. First, we look for products that are making newsworthy claims, things like very fast charging, very high pulse current, high energy density, longer cell cycle life, things like that. But then that's often related to some very specific technical innovations that are claimed. Things like composite anodes, separators with nanoparticles, butterfly form factor battery packs, form factors of the actual cells, for example, the Tesla 2170 or the newer 4680, cell structures such as tablets designs within the cell, as well as protection control modules. As an example there, Xiaomi has been recently talking a lot about their Surge P1 chip in the M112 or in the Mi 12, which is enabling very fast charging rates while claiming maintaining a long battery cycle life. We're also interested in when things go wrong. As an example, product recalls. We have an ebook available on the Chevy Bolt. You can download it if that sort of thing interests you. And right now we're also tracking 2 other recent devices that are experiencing issues. And finally, we're also watching to see if product manufacturers are moving to support right to repair. Because from a battery perspective, this will fundamentally change how the batteries will need to be incorporated into the product, as it will have implications on the physical fit, heat, safety, those types of things. Now, with that background, let's take a step back and look at the types of battery analysis we're providing. To start with, you can see 4 levels of analysis moving from the left to right. You can see that the 3 types of analysis are available now, and the 4th is still in incubation, which means it's not available yet, but we're targeting that for second half of 2022. Now, starting at the left, we have portable battery teardown. This is really product level analysis where we show which packs, cells, and charger ICs are found in a range of real world products, be it phones, wearables, tablets, laptops, etc. And looking at 2020 and 2021, we have over 400 consumer electronics products profiled. By the end of 22, we expect that number to be closer to 600. The second is battery essentials. And this is really focused on 3 things specifically around the battery pack and cell. How does the battery actually fit into a real product? And the second thing is, what are the cell's key structures? For example, how are the electrodes wound? What does the tab design look like? That sort of thing. And then the third is really around cell materials analysis, be it the anode, the cathode, separator, electrolyte, cladding, etc. We do a deep analysis of the composition. The next 2 types of analysis are completely different in that they measure actual performance characteristics of the battery cells. Battery characterization gets into the details in terms of charge thermal analysis, DCIR, OCV curves, DQ over DV, EIS, and charge discharge characteristics. And the last one, the battery cycle life, is testing where we actually track the cell's aging characteristics all the way to end of life. And while doing this, we're also measuring cell expansion, as that can be a troublesome issue as new chemistries are released. These cycle life tests are more challenging for us because they need to span typically a number of months before we fully exhaust the batteries. So if we were to summarize all that, essentially we have 4 subscriptions that describe who is winning, how is the battery cell built, how well does it work, and how long will it last. And to bring this back specifically to today's presentation, all of the materials and the discoveries that we're showing came from the second subscription called Battery Essentials. A few slides ago, I showed you the criteria we use when looking to determine which cells we should analyze. The next 2 slides are going to highlight some of those recent innovations that we profiled. For example, looking back to last year, we took a look at the LG Chem battery involved in the $1.9 billion Chevy Bolt recall. We also looked at the product claiming to be the first graphene phone. This was the Xiaomi Mi 10 Ultra, which supported 120-watt charging. We also wanted to cover a Samsung battery, as they are an industry leader in both the smartphone segment as well as battery technology. We also looked at a power bank that claimed to be the fastest charging and claimed to use graphene-based cells. We also looked at an RC racing car that supports 135C pulse discharge. The next one was interesting because we found a power bank claiming to use a Panasonic lithium graphene composite 21700 cell, the one used by the Tesla Model 3. And lastly, the next Xiaomi phone came out, and it was the Mi 11 Ultra, which claims to be the first silicon oxygen anode phone. So before jumping to the next slide, you can see that the last two products are two of the products that are going to be discussed at a deeper level today. And now looking at this year, we continue to see significant battery innovation. Sila Nanotechnologies is releasing their chemistry in the Whoop 4 fitness tracker. It's claimed to be the first product using next generation silicon anode materials. The Fitbit Ionic, on the other hand, is a 2017 product, but we're profiling it because it's going through a recall due to heat issues, which resulted in some consumer burns. Realme, the smartphone manufacturer, is taking charging to a new level with the first 150-watt charging phone. And the Fossil Gen 6 smartwatch also is exhibiting some complaints in terms of charging and heat issues. So we're watching that one very carefully. Xiaomi continues to push forward with new chemistries. They have something called high silicon lithium supplementation, and they claim this is allowing them to increase the silicon content of the anode by a factor of 3. Google is releasing their very first smartwatch, the Pixel smartwatch, which is expected this fall. So we're watching that one. And finally, Murata is claiming they will actually have a solid state battery commercially available, targeting IoT and wearables market with a capacity ranging from 2 up to 25 milliamp hours. So we're watching for that. Now, if you look at the top, you can see the third product that we will be profiling today. That is the Sila Nanotechnologies technology found in the Whoop 4. Now, this is a roadmap, meaning that since we're still early in 2022, it is flexible, and we are looking for suggestions on different products that we should be profiling. This concludes my section covering the market. I'm happy to pass it over to Ali, who will get into the details on his findings on the silicon anode technologies found in the 21700 powered power bank, the Xiaomi Mi 11 Ultra phone, and the Whoop 4 fitness tracker.
Thank you, Trevor, for the introduction and the market info. Hello, everyone. First of all, I would like to thank you for attending this webinar. In my talk, I will present some of our interesting findings from analysis of the silicon-based anode batteries of Panasonic NCR21700, Amperex BM55, and WS40, a cell made by Sila Nanotechnologies. With an ever-increasing demand for energy storage for portable, wearable, and electric vehicles, extensive research is focused on enhancing the lithium-ion battery technology by reducing cost and improving the performance. By 2025, industry targets an energy density of the 350 watt-hour per kilogram at the cell level. This target leads to an ongoing attempt to improve the main components of the lithium-ion batteries. In correspondence to the main component of the cell, the technology roadmap of the lithium-ion batteries can be grouped into 5 main areas, including cell design, novel materials for the cathode, novel materials for the anode, improvement in the electrolyte, and modification of the separators. This image shows the technology roadmap of the lithium-ion batteries used and developed by TechInsight. As we saw from the previous chart, one of the mainstream the technology advancement is focused on exploring and improving the battery-specific capacity and rate capability by introducing new materials for the anode, particularly silicon and graphene. Here it should be noted that lithium metal batteries can be considered separated from the lithium-ion batteries, since there are substantial differences in electrochemical phenomena at the anode of this battery. Back to silicon and graphene topic. In early 2017, the commercial application of silicon and graphene was introduced. Currently, the silicon to graphite ratio is around 10% for commercial cells, and it is expected to develop a pure silicon anode by the end of 2025. Although the application of silicon and graphene can increase the energy and power densities of the lithium-ion batteries, there are a few obstacles for each technology. This table summarizes those innovations and obstacles. While for graphene technology, the main concern is the cost, the main issue is related to cyclic performance for silicon-based technology. In this webinar, we present the practical implementation of the advanced silicon anode technology from NCR 21700 cells, a cell made by Panasonic and Tesla, ATL BM55, a cell from the Xiaomi Mi 11 Ultra phone, and WS40, a cell made by Sila Nanotechnologies extracted from Whoop4 fitness tracker. Before characterization of these three key products, let's have an overview on motivation of application of silicon in the anode of lithium-ion batteries in this slide. The most used anode material for the lithium-ion batteries is graphite, which has a specific capacity of 372 mAh per gram. However, the energy density of the battery can be improved with incorporation of silicon instead of graphite. Silicon features a high theoretical specific capacity of 4200 mAh per gram, which is more than 10 times higher than that of the traditional graphite anode. However, there are challenges in using silicon as it is prone to significant volume expansion and contraction during charge and discharge cycles. These volume changes can cause cracking of the active materials and lead to an unstable solid electrolyte interface. These challenges have prevented silicon from being broadly used in commercial rechargeable lithium-ion batteries. To overcome this problem, several solutions have been introduced in the industry. The first one is the application of the silicon oxide instead of pure silicon. Silicon oxide undergoes lower volume expansion during cycling than pure silicon, but still, it has 3 times higher capacity compared to graphite. The second approach is to synthesize silicon particles with smaller sizes, in fact going to the nanoparticles, to alleviate the cracking issue. However, a promising method to develop a stable, high-capacity anode is taking advantage of the stability of the graphite and combining it with the high capacity of the silicon and silicon oxide-based materials to create a composite anode. Compared to graphite alone, hybrid materials poses a higher specific capacity and good cyclability and long-term stability. But it doesn't mean that there is no. It doesn't mean that it prevents the industry to go for the pure silicon. In fact, Tesla aimed to develop a raw silicon anode batteries for their EV as they announced in September 2020 in their battery seminar. This slide shows an overview of TechInsight's material characterization used for this study. As we know, silicon graphite composite can synthesize in different ways, as shown in the left figure. Ball milling, spraying, wet process, and plasma treatment are the most common methods. Now a question arises here. What are the criteria for choosing a method among all these techniques? The answer is not easy, but we can say it mainly depends on the silicon and graphite source plus the desired silicon ratio. At TechInsight, we performed several analyses to characterize the silicon-based technology. These analyses are focused on the graphite particles, such as width, diameter, and shape of the graphite, using planar and cross-section SEM and EDS test, XRD, Raman spectroscopy, also focusing on the silicon particle details, for example, width diameters of the silicon-based particles, the oxidation states of the silicon particles using XPS, using planar and cross-section SEM EDS analysis plus XRD. and also the binder characterization using SEMI-DS, FTIR, TGA, and XPLs. By gathering this information, we could also comment on the synthesizer strategy, such as ball milling and wet processing. Now let's back to our case study batteries. The first one is Panasonic NCR21700. This battery was designed for Tesla Model 3 and it has been used by Charge ASAP for Flash 2 power bank. This battery is one of the earliest silicon anode battery in the market. The second one is the battery of the Xiaomi Mi 11 Ultra. Xiaomi claims it is the first smartphone that uses the second generation nano silicon anode material, leading to a 10 times higher capacity than traditional graphite anode cells. Thanks to the silicon technology, this battery is set to charge to 100% in 36 minutes. The third one is the battery of Whoop 4 fitness tracker made by Sila Nanotechnologies. Sila Nanotechnologies Incorporation is a US-based company working on developing silicon nanoparticles to enhance the lithium-ion battery's capacity. Sila claims their new anode composite material increases the energy density by 20% today and up to 40% improvement in the future releases. They also believe that their Sila nanotechnology can support full graphite replacement to achieve maximum performance or partial graphite replacement for faster speed to market. Recently, in fact, last month, Sila started a collaboration with the Mercedes-Benz for the EV type of Mercedes Class G. These three pictures show the cross-section image of anode electrode of Panasonic NCR21700, Amprex BM55, and WS40, the cell made by Sila Nanotechnologies. By comparing these images, we could track the evolution of the silicon-based technology for lithium-ion batteries. In Panasonic NCR21700, silicon particles are present in larger size than BM55. In WS40, the silicon exists in spherical microparticles, which is a breakthrough compared to the BM55 and NCR21700 cells. In BM55 and NCR21700, silicon is randomly distributed in the active material, suggesting a ball milling process. However, in WS40, the microparticles are connected through a network mainly made up of carbon. This figure shows that the silicon ratio is highest in WS40 compared to NCR cell and BM55. These same images shows the planar view of the anode. Based on these images, we can say that the content of the silicon-based particles in BM55 cell is lower than NCR21700. They also show that in BM55, both graphite and silicons are smaller compared to NCR21700. To have further details on the source of the graphite, XRD analysis and Raman spectroscopy are required. With respect to WS40, we can see the spherical silicon particles confined between the graphite flakes. We perform additional material characterization on these electrodes and the results are summarized in next slide. In detail, we performed XRD and XPS and Raman spectroscopy on the anode of these samples. In summary, we concluded that the anode of these batteries were synthesized using different methods, most likely ball milling for NCR21700 and BM55 cells. With respect to WS40, the results reveal several innovations compared to NCR21700 and BM55, including application of micro-silicon-based particles, as we know, smaller better. A scaffold structure versus random distribution of the silicon particles. In fact, the silicon particles are connected through a network. A different oxidation state of the silicon in the silicon-based particles. In WS40, the oxidation state of the silicon is different from the NCR21700 and BM55, but still, it's not pure silicon. The presence of a ceramic additive to improve the properties of the SCI layer. Also, the presence of the nanoparticle as a binder to keep the integrity of the anode and cathode layers. These nanoparticles are shown in this figure. Now we have this question: what are the advantages of this electrode compared to other methods? The first one would be the better cyclic performance. And the second one is that this method can provide a promising way to increase silicon-carbon ratio. This structure acts as a brittle structure. In fact, silicon particles are supported by this network, and volume expansion contraction can occur in a more pseudo-plastic environment. However, to make sure these claims and investigate the superiority of each method, we need to subject batteries to an actual cycling condition. That's why we also introduce a new subscription aiming at battery characterization in the next slides. Battery characterization includes several tests on system level and cell level. System functional test gives insight to the current, voltage, and thermal mapping of the points of the battery, multiple points, ICs, PCB, while the battery is inside the device and is charged using a cord or a wireless charger. In the functional cell test, we focus on the electrochemical response of the cells, including open circuit voltage versus different state of charge, internal resistance measurement using electrochemical impedance spectroscopy at different state of charge, and DCIR methods. We also provide insight into the chemistry of the cell using differential capacity analysis, or known as dQ over dV map. We also investigate the effect of the temperature and discharge rate on the discharge capacity of the cell. Battery cycle life is one of our in-progress subscription aiming at characterization of batteries over cycling. It includes standardized CCCV charge, CC discharge cycles coupled with reference performance tests, direct current internal resistance measurement, and electrochemical impedance spectroscopy. The standardized CCCV charge and discharge cycles are adopted from the standard device operation. It is possible that during the cycling of the cell, the soft pouch expands due to gas generation because of the side reactions. To track the cell swelling profile, X-ray images are taken every 100 cycles from different angles at least 6 sides of the battery in comparison to that of at the beginning of the cycle life.
Thank you, Ali, for the informative overview and analysis. We hope you enjoyed this webinar and welcome your feedback. Given our battery subscriptions are new and the market is dynamic, your feedback is particularly important. For example, are there specific devices you'd like to see analyzed? What other battery analysis would you like to see? Your comments are extremely important. Please complete the feedback survey, which will be automatically presented to you at the end of this webinar. So why choose Tech Insights? Founded in 1989, Tech Insights offers an unparalleled combination of the latest technologies and analytical techniques, knowledgeable subject matter expertise in the broadest range of technologies, and the world's largest database of semiconductor analysis created over our 30-plus years of operation. We serve our global clients from our headquarters in Ottawa, Canada, as well as from a number of satellite locations around the world. And with that, we'll start the Q&A portion of our webinar. To submit a question, click the Question tab and enter your question in the text box. If you would like to learn more about Tech Insights battery subscriptions, you could email us at info@techinsights.com or visit our website www.techinsights.com.